Okay, so today I'm going to cover optics for MCAT, for the MCAT, physics MCAT. And you have two subtopics. You have the geometrical optics and then you have wave optics. And I have a playlist in my channel where I cover the geometrical optics. Okay, so some of the problems are a little bit tricky, so let's go over them. I have saved them here. So here is the first question. You can always pause the video. Okay, so they want to know if you know the terminology used in optics. So it says which one will not cause white light to break down in individual colors, right? So you have diffraction, refraction, reflection, dispersion. So just as a review, and again, you can pause the video. You have three here properties of light. In geometrical optics, you have refraction. So when it happens when light goes from one medium to another one, it's going to bend, okay, or refract. So when it goes from air, where it's moving at the speed of light, to water, so it's going to move slower. And then to air, you see, it's going to be refracted. Light can be reflected, so it's like bouncing off. And light can be diffracted. So here it means it's going to bend around corner. Okay, so you have refraction, reflection, diffraction. Okay, so let's see. Here it says, if there is a prism, can you have a breakdown into its individual colors? Yes, of course. With a prism, that's the very basic thing, right? So if you have a prism, let's say 49, slide 49 here. So if you have a prism, that was the experiment done by Newton the very first time. He used a prism. He used white light from the sun, for example, and you see that he was able to break out light into its wavelength, right? Its components. And you see that blue light will bend more than red light. That's why you have this dispersion. So you have refraction here, and then there you have dispersion because you have the rainbow. Okay, so blue light bends more than red light. So I'm not going to teach why, because I have a playlist about it. It has to do with the speed of light in a medium like glass depends on the wavelength. So blue light will have a slower speed into that medium than red light. Okay, so anyway, it's not A. Okay, can you have a rainbow, for example, with diffraction through a grating? So this is called diffraction grating, actually, and that's how we do it in lab, right? We don't use a prism, we use a diffraction grating. And what's happening here, light will bend around the corner, so it's called diffraction, but the bending depends on the wavelength. So it depends, so yes, so you're gonna have a breakdown, and of light, and it's gonna be diffracted at different angle depending on the wavelength. Okay, so this is a closely spaced slit, okay, that will diffract light. So anyway, if we go back to here, diffraction for a grating, yes, you're gonna get a breakdown in different wavelengths, so that's not it. Can you have color with a thin film? Yes. Okay, so you are very familiar with this phenomenon. right? So if you have a film here, light will be refracted, and again, it will, you're going to see a rainbow. Okay, so if I go back to my slide here, I don't know if I have it here. Maybe, I don't know, I have so many slides, but now this is reflection, and here, okay, so this is the experiment done by Newton, by the way. Here he put a prism, but I cannot find the slides because I have so many. But yes, with when light goes through a thin film here, okay, you have the picture here. It goes through glass. It goes through a layer here. So you're gonna have diffraction here. Okay. So this is the thin slice here. So it could be a soap or oil, for example, oil like from the car on a puddle of water. And you see it's gonna be reflected here, refracted, reflected. So you have different colors. So it's not that answer. What about reflection? So reflection, no. Okay, so reflection is just bouncing off, and all the wavelength will have the same reflection angle. Right? So if you look at reflection here, you see it's bouncing off, and there is no breakdown into colors, right? So all the wavelength will be reflected exactly with the same angle. So this is the incidence angle, and that will be the reflection angle. Okay? So the only answer is D. Okay, so it's kind of tricky question. You need to know your stuff. Okay, so let's go to the next one. That question requires that you don't jump on the equation, Snail's law, but you need to do a drawing first, right? So again, you can pause the video and try to do it. Okay, it's fine. So if you want to have a better understanding, you can always use this. It's free simulation FET, right? And it's about refraction. You see here when light goes from air to something thicker with a larger density. Okay, so it's gonna be reflected. Some of it will be reflected, and some of it will be refracted. So if you go from fast, so larger speed to slower speed, low density to higher density, light will be refracted toward the normal. Okay, so it looks like this. Okay, so here you go from air to glass. Glass has an index of refraction of about 1.5. So that means the speed of light in glass will be divided by 1.5. And you see, it's very cool because you can see that will be the speed of light. C in air is about C. And here it's going to be less. Okay, it's going to be divided by 1.5. Okay, which is two-thirds of the speed of light. And you can see some of it will be reflected, 11% here, and 88% will be refracted. So it's very cool. So anyway, I don't know where I was here. So you have to do the drawing. Okay, so you go from air to glass. So already you know this is fast and this is slow. You always draw the normal. And you see 60 degrees. So 60 degrees, let's say this is 60 degrees here. So this is 60 degrees. And then it says the angle between the reflected and the refracted ray is exactly 90. So they want to make sure you understand that. Okay, so they talk about reflected. So reflected means it's going to reflect back, and this is 60. And you know that the refracted has to be smaller angle, right? And they tell you that between this and the refracted angle, it's going to be 90 degrees. So I'm going to make a kind of 90 degrees here. So this here is a right angle. So this is 60. So that must be 30. If this is 90, that must be 60. So that will be 30. Okay, which makes sense because you want a smaller angle here, right? So if you go back to the here, so here it's going to be about 60. And here it's about 30 degrees. It depends on the material that you have here. So about something like this. Okay, what is the refractive index of the glass? So here you have N1 equals 1 because it's air, and here N2 equals question mark. Okay, so we're gonna have Snell's law. So you have N1 sine. So that will be the incidence angle equals N2 sine theta 2. So this is your theta 2. So N1, so 1 times sine 60 equals N2 sine 30. Okay, so N2 is sine 60 over sine 30. So sine 60, you need to know that by heart. It's square root of 3 over 2. You divide by sine 30, it's 1/2. You multiply by the reciprocal. Okay, so N2 is square root of 3. So the answer is D. Okay, so those questions little bit challenging. You just have to draw. Okay, so next question. So let's look at what's a compound microscope. Again, compound microscope here. You see, you have more than one lenses. More than one lens. It's a compound microscope. And it's just to know the equation. It's just when you have a compound microscope, the magnification will be just the multiplication of both. Right? So that means that the magnification is just M1 times M2. So in that case, it's going to be 400. So that will be answer D. So magnification is the height of the image over the height of the object, which is negative the distance. So this is magnitude, the distance between the lens and the image and the distance between the lens and the object. So that's just the definition. Okay? So that should go easy. Okay. So this one is just that you do not have calculator, so you need to know some tricks, right, to do it, to find the answer. Okay, and you need also to know equations. Okay, so you should stop the video and try to do it here. Okay. So they want the ratio between the speed. The speed in a material is going to be c, the speed of light, over the index of refraction or the refractive index, right? And c is the speed of light in air or in vacuum. It's about that. Okay, so that's the definition. So what's going on here? So you have from n sub 1 to n sub 2. Okay, so the incidence here is 30, and then 30, and now it's going to be 45. Okay, maybe I should make 30 smaller. So here it's 30 degrees, and here instead of being 30 degrees here, it's going to be 45. So because that angle here is larger than that angle, it means that the index of refraction will be larger, right? It's going to be larger. And you can see that if you go back to that here, if I do the opposite, if I do glass here, if I do glass, and okay, air. No, it's the opposite, right? Sorry. What did I say? Here, it's the opposite. So because it's larger, that means this material here will be thicker with a larger density. So we expect N1 to be larger than N2. Okay, so the velocity here, V sub 1 should be smaller than V2. Okay, and now let's go back to here. You go from thick to not thick. Here, and you see that that angle here is smaller than this angle there. Okay? Here, about 45 degrees. This is about 30 degrees. This is about 45 degrees. So this is more dense. This is less dense. Smaller speed, larger speed. Okay, so after we have clarified that, so what do we have? We can apply Snell's law. So we have n sub 1, and then we have sine 30 equals n2 sine 45. So we want a relationship with n2 and n1. So n1, so sine 30 is going to be, what is sine 30? It's going to be 1/2. And 2, and that's what you need to know by heart, right? Sine 45 is the square root of 2 over 2. Okay? So you see that n1 over n2 is square root of 2. Okay? And what else do we know? We know that the velocity here, 1, is c. over N1, and V2 is C over N2. Okay, so that means that we want V2 compared to V1. Okay, so that means I'm going to write here. So that means that V2 over V1 equals 2. So C over N2 multiply. So when you divide, you multiply by the reciprocal. C, boom, boom. So it's going to be N1 over N2. Okay, so we have this ratio here. So it's going to be square root of 2. So 1, and that's going to be 2. So the answer is V2 equals V1 square root of 2. Okay, so that means V2 equals square root of 2 V1. Okay, so the answer is A. Okay. So which one can produce a virtual image? So we have convex. Yes, it can produce a virtual image. Concave, plane mirror, all of them. Okay, so convex, concave, plane mirror, obviously, it's not a real image, it's a virtual image. So the three of them. So the answer will be D. So again, you can use PhET, which is convenient. So you see here, you have the image. The image here is real, okay, because it's not beyond the mirror. If you bring it here, boom. So that will be virtual. And that's concave. A concave mirror. If you have a convex mirror, you always have a virtual image upright here. And if you have a lens, so if it's convex, if the object is inside here, so that will be the focal point, it's going to be virtual. And you have a concave mirror, so then the image is always virtual. So answer is 3. 1, 2, and 3. Okay. So for this one, you can pause the video and try to answer the question. So it's a single slit diffraction. So that takes you to the wave property of light. So any wave can diffract when it goes through an opening. So it means it bends around the corner. It's true for sound, water, and light. So what's going to happen if you change the width of the slit? What happens to the width of the central maximum, right? So the fringe that you see on the screen. So again, we can look here. You see when light goes through an opening, it's gonna diffract. So that will be the maximum fringe that you see on the screen. This is the intensity of light, okay? And it depends on the wavelength, and it depends on the distance, obviously, and it depends on the opening of the slit. Okay, and there is an equation for that, but I will show you an app as well. So it's gonna be called the single slit experiments. So that will be your maximum here. That I will show you. But the width, we can see that the width of that width here, right, is 2 times Here it depends on the distance. Okay, because if you increase the distance, of course, if you move back the screen, the size of your spot here will be larger. So it depends on the wavelength. So it means larger wavelength. It's like it's going to feel more the corners, right? Wavelength, you can think of that. So what's a wavelength? It's when you have a wave. It's a distance between two crests. For example, it's like the size of the wave, right? So you see, if you have a large wave, it's going to feel more the corners. So it's going to spread out more. Okay. But it's also inversely proportional to the width of the slit here. Okay, so it means if the slit decreases, omega will increase. And I can show you that. There is this great simulation here. So it's called FET, wave interference. So it doesn't matter. It happens for sound. Sound is a wave. It goes through an opening. It's going to spread out. Okay, especially if the opening is smaller than the wavelength of the sound. That's why even if you are standing here behind the wall, you will hear whatever it says. So anyway, it's true for sound, it's true for water, and it's true for light. So let's take something you can really see. Let's take red light and let's open the opening here. The slit, you have red light. So you see here the distance here. It's like you are looking at light from above. So the size of the wave, this is the wavelength, right? So it will be between two crests. This is the throw. So as it goes through the opening, here it's going to spread out, but not that much because the opening is really big. And you can put a screen here and you're going to see that. So here it's not too surprising. Red light goes through here. It's going to spread out, but very little. You can even look at the intensity here. But as you decrease the size of the opening, so then light will spread out more. You see how it's going to increase here? Because it's spreading out more. So it's going to be called diffraction. So it's spreading all over, right? So same intensity, but it's spread out more. And it gets worse as I decrease the width. So then everything will be red here, which is surprising. Not intuitive, I mean. So anyway, it's a wave property of light. Here, so what happens if you decrease the width of the slit? So the central maximum becomes wider. So C is the answer. And you also have relationship. Okay, so a marine physicist. From beneath the water toward the water surface. So it means you go from high density to low density medium. Internal reflection and do not pass into the air above. So here they want you to find the critical angle. Critical angle. So you can go back to your lecture. But you see, when you go from slow to fast, okay, here, no problem. You still have refracted and reflected, but when you're going to hit the critical angle, you see this refracted beam get closer and closer to the interface. When you hit, boom, you see, when you hit the critical angle, which is about 44 degrees, everything will be reflected. So this is called the critical angle, and that's what they want you to find. Okay? So let's go back to here. And again, you cannot have a calculator. They give you the refracting index of water. So maybe you want to draw. Okay, so you have an interface here between water. So this is water. And so 1.33. And this is air. And at an angle here, we don't know which one, but at an angle, okay, so this angle here, that's what you want. It's a critical angle. Light will be here. So it will be 90 degrees. If I go smaller than that, then it will be reflected. It will be refracted. And as it gets closer to the interface, after that, everything will be reflected. So this is called the critical angle, and that's what they want. So we use again. So this is 1. So you go from 1 to 2. Sine theta 1 equals n2 sine theta 2. So in that case, that's going to be 1.33 sine your critical angle equals 1 times sine 90, which is 1. So you have sine equals 1 over 1.33, and we cannot have a calculator, so we need to find a different way to do it. So it will be 1. So what is 1.33 is 1 plus 1/3, right? Or 4/3, right? It's going to be 1 over 4 over 3, which is 3 over 4. Okay, so we need to find a way to manage without the calculator. So 3/4 is about 0.75. Okay, so which answer should it be? And you know that sine 45, for example, is about square root of 2 over 2, right? Which is about 0.7. So 0.7 is smaller, right, than 0.75. So you need an angle. So the angle theta has to be larger than 45. So you need to find a way without a calculator. So the answer should be 49 degrees, right? Because sine, you see, if you look at the sine, as the angle is going to increase, it's going to increase. So 45 degrees, here it's going to be 0.7. So 49, it's going to be more than 0.7. So closer to 0.75. So the only answer will be D. Okay, so polarized, unpolarized. So you can take you can look at the question. So light, so again, it's the wave property of light. So light, you can think of light. Sometimes it will, oh, here we have, see, polarized. So light will vibrate in all direction, all random direction. So if you put a polarizer here, you're going to force the light to vibrate only in one direction, so in one plane. And if you have a second polarizer, so it's going to be blocked. Okay, this picture tells it all, right? If so, here you have light vibrating in all directions. So then you have a polarizer, so you force it to vibrate only in one direction. And then here, if you have another polarizer at 90 degrees, you see the slits here are 90 degrees, then you are blocking all the light and there is no more light, right? That's how Polaroid works. I don't know if I have another. You see here, so the light coming from a screen is polarized. So here it's fine, but if I place it at 90 degrees, there is no more light. So this is called polarization. So anyway, so if you have two polarizers and they are 90 degrees from each other, so then there is no more light that will get through. Okay? Okay, so let's look at the next one. Converging. If an object is present in front of the lens at a distance less than the lens focal length, which one of the following describe the resulting image? So convex is converging lens. So it's like a magnifying glass. Okay? Magnifying glass. If you bring a magnifying glass very close to a piece of paper, you're going to see things upright but virtual. So the answer is virtual and upright. And again, you can use the simulation here with the lens here. So this is concave, this is convex or converging lens. So if you bring the object, like something written on a piece of paper very close inside the focal distance here, so this is focal distance, this is a focal point, the image will be virtual upright. So you will see something bigger. Okay, so the answer is B. Okay, and then I don't know what's going on here. Chromium. Okay, so first of all, when light is refracted, the frequency does not change. So it means the wavelength has to change because the speed changes, but not the frequency. Okay, so you have the speed of light is the wavelength over the frequency. So when light goes inside the medium with a larger density, density, so it has an index of refraction larger than 1, the speed will decrease by a factor. It will be divided by n. Okay, so if so the speed is the wavelength. Sorry, I made a mistake here. The speed is the wavelength times the frequency. Okay, so the speed of light or any wave is the wavelength divided by the period, which is the wavelength times the frequency. So anyway, if the speed decreases by a factor, a given factor, right? If it's divided by L, so it's the wavelength that will decrease. And because when you have red light going through a window, for example, or you're looking at a tree, it's green. Okay, the color has not changed. So the color does not change, the frequency does not change, only the wavelength will change. Okay, so again, you can go back to this excellent bending of light. Okay, you can look at the wave here. So if it goes from air to glass, for example, you see that the wavelength is decreasing. Okay, the distance between two crests is smaller here, and the speed is decreasing as well, right? Speed has decreased, but so it's 60%, so 40% less, but the color does not change. This is red light and this is red light. So anyway, my point is it cannot be this, it cannot be that, it's either this or that. And then we are looking at through air into a block of crystal. Okay, so let's make a drawing here. Without drawing, it's hard to see what's going on. So through air into a crystal, so you go, this is air, this is crystal, and this is chromium. So it's 1, 2, 3. So it enters the crystal at an angle of 30 degrees. Into the chromium. So this is 30 degrees. So that will be, crystal will be a smaller angle, right? Because it's going to be slower. Into the chromium. So we don't care what's going to happen here because it says light emerge not from the chromium, but into the chromium. So they are looking at this angle here. And because N2 is larger than N1, that means that that angle here has to be smaller. Okay, so it's going to bend toward the normal. So the only answer then is A. Without doing any computation, it's just that you have to be very careful with the reading. So it's more like reading comprehension. Okay. So this is the same question as before, because you have 3 polarizers aligned with each other, and the third is rotated 90 degrees. So they try to trick you, but it's the same idea. As long as you have one, which is 90 degrees to the other one, then you're gonna get only one direction here, and then you put another one, it's gonna be, it's gonna stop. Then there will be, so you have 2 polarizer, one is perpendicular to the other one in orientation, so there won't be any light here, it will stop the light. Okay, so it's just they try to trick you with 3 of them, but the answer is still, it's not going to get through. Okay? Okay, so here some red Okay, so that means, so first of all, they ask you to, you need kind of know the wavelength and the frequency of visible light. For visible light, you always have something around 10 to the 14 for the frequency, and for the wavelength, you don't need to know exactly the number, but you need to know that red has a larger wavelength than blue. So because you have two choices, it has to be 700, right? Red has a larger wavelength than blue. So you need to kind of know the electromagnetic spectrum, right? So electromagnetic spectrum. So first of all, I don't know if maybe this one. So you see here, red, the wavelength is about 700. Blue, the wavelength is about 400. You don't need to, that one had a very nice picture, but it won't let me click on it. Maybe this one. I don't know, I cannot click on it. But you see, you go from gamma ray, small wavelength, large frequency, and then as you go, so all those are the bad guys. So high frequency, high energy, small wavelength. And then you get to the blue because you have UV, so blue here. And as you go from blue to red, you increase the wavelength, you decrease the frequency, and keep going here, increasing the wavelength and decreasing the frequency. Okay, so that's how you could have said it should be 700. So frequency here, so if you look again at you see frequency of red is about 10, 4. So it's 4 times, about 4 times 10 to the 14 hertz. So that also is correct. Or actually you have two answers, right? Right. You have the wavelength of 700 and 10 to the 14, 4 times 10 to the 14 hertz. So I'm not sure they will ask you to memorize this, but it's good to know anyway. Okay, so now we have seen the single slit experiment, and now it's going to be the double slit experiment. So you need to know the equation. This double slit experiment, it's a very famous experiment because that's an experiment that shows that did show at the time that light behave like a wave. It can behave like a particle. That was shown after that by Einstein, but before that, you see, you had this very famous Young's double slit experiment, right? So you see what you get. Light goes through two slits, and then you have a pattern here, dark, bright, and so forth, and so on. And you have equations here. So you can do also this one if I have two slits. That's a double slit experiment. So I have a pattern of no light. So this is because of interference, right? So here you have destructive interference, which means light destroys itself. And here you have constructive interference, light coming from both reinforce themselves. That happens with sound, can happen with sound, and can happen with water as well. And the equation for that, so this is for the bright the position of bright fringe starting from here. So m equals 0, m equals 1, m equals 2. And this is the black or the dark fringes. Let's say what they want. So 30 degrees. So it's the second dark fringe that appears at an angle of 30 degrees. So it means dark, dark. So from here to there, it's going to be 30 degrees. Not this one, but that one. So you need to use that equation here, right? So you can pause the video, try to do the math. So by the way, if you're interested, this slide comes from Cutnell and Johnson, Physics. From Cutnell and Johnson, it's the book I recommend for the MCAT. Cutnell and Johnson, and that's a slide from the book, right? So we want m equals 2. So this is 1 and this is 2 here. So m equals 2. Okay, and the angle here is 30 degrees. So we have sine 30 degrees is 2 plus 1/2 lambda over, and what do they say? Lambda is the wavelength. That's what you want, and the width is 0.3 millimeter. So lambda over the width, so 0.3 millimeter. Okay, so that will be the distance between the two slits. So if you go back to here, D is the distance between the two slits. So that distance here, and this is the angle. So here I have to move this to the 1, 2, 2 here. Okay, so you're using this equation here. Okay, so we have that. So sine 30 is, so it's gonna be 5 over 2 lambda 0.3, and 0.3, this is millimeters, right? So this is distance, so it's good. So that will be 1/2 equals 5 over 2 lambda over 0.3. Cross, cross. So lambda equals 0.3 over 5, 0.3 over 5 millimeters. And 30 divided by 5 is 6. So 3 divided by 5 is 0.6. So 0.3 divided by 5 is 0.06. So lambda is 0.06 millimeter. So this is 10 to the negative 3, and then 4, and then 5. So it's going to be 6 times 10 to the negative 5 meters. Okay? So answer is this one, B. Answer is B. So again, you need to know your frequency. So 10 to the 14, as I've said before, 10 to the 14 is visible light, right? Visible 10 to the 14. UV, you're going to increase by a factor 10 or 1000. That's X-ray, that's gamma ray, and then the other way, it's going to decrease. So you need to know, apparently, that visible is about 10 to the 14 hertz. So the answer would be 5 times 10 to the 14 hertz. It should be visible light. Okay, so the answer is visible. Okay, I have another series coming on optics, but today it's